Good evening, everyone. So I welcome you all in a Sapiens Education. So today I'm going to solve question number 7.16 of the chapter the gravitation. So gravitation, this is a gravitation chapter. So we need to discuss this thing. Okay. Now assume that the question they are asking, assume that the Earth to be the sphere of a uniform mass density. How much would a body weigh halfway down to the center of the Earth if the weight is 250 Newton on the surface? So let us draw the earth surface. This is a earth, and there is a body at the top of the earth. So this is the body at the top of the earth. We can also change the color. Here this is the body. And this is the body, and it has a weight is equal to weight, that is W is equal to 250 Newton. Now they are asking that we need to find the weight when it is down, when you go deep inside the earth's surface. So at this point, if the object is kept here, so we need to find the weight at this point, that is W dash, that is W dash. Okay, W dash is equal to what? Okay, so this is the question. Now as we go deep inside the earth surface, side the earth surface, gravity decreases, right? So new gravity have a relation G is equal to 1 minus d by radius of the earth. Okay, so this is the relation for new gravity. Now as per the question, the depth is equal to radius of earth by 2. So the gravity new dash, that is G dash, is equal to G into 1 minus Re divided by 2 into Re. So finally it got cancelled out, so this will be G by 2. So G dash is equal to G by 2. Now the question is that what is the weight at this point? So weight W dash is equal to m into G dash. But what about mass? So mass is equal to weight by gravity. From here we can find 250 divided by 10. So this will be approximately 25 kg. So we have got the mass. So finally if you got the mass, so we can easily find weight W dash. So W dash will be equal to mass, that is equal to 25 into G dash. G dash is equal to G by 2. So finally 25 into 10 divided by 2. So this will be 125 Newton. So this is the new weight. So finally the weight which is at this point, which is at a distance of half of the radius of the earth, is equal to 125 Newton. Okay, so I hope you have understood this question. So now we will solve question number 9.17. So what they are asking, in 9.17, a rocket is fired vertically with the speed of 5 km per second from the earth's surface. How far from the earth does the rocket goes before returning to the earth? So the initial velocity vi is how much? Vi is, they have given vi as a vi, initial velocity is equal to 5 km per second. So if a rocket has been projected with the speed of 5 km per second, so at a certain distance what will happen? It will again come back toward the earth. We need to find this height plus this height. Not only this height, we need to find the height from the center of the earth, because they are telling that In question they are taking how far from the earth does the rocket go before returning to the earth. So it means that we have to take the reference point as the center of the earth, so we have to take this height as well as total height as d. So we have to find d only. Okay, no issue at all. So we can now use work energy theorem. Work energy theorem, that is total energy will be conserved, total energy will remain conserved, energy will be constant, remain constant. Okay, now here see we have a initial kinetic energy plus final kinetic energy at this point when the object when the rocket is at this point. So we have initial point and this is your final point. So initial kinetic energy plus plus initial potential energy will be equal to final kinetic energy plus final potential energy. But you know that when a rocket when this rocket will reach this point, so after that it will try to return, because at this point the velocity of the rocket will become zero. So at this point kinetic energy, that is final kinetic energy, will become zero, right? Now we need to find the rest of the thing. So initial kinetic energy means what? Half, we can write here half into m into v square, that is velocity of the square, minus g into capital M in small m by radius of the earth. So this is the potential energy, and this is equal to final kinetic energy 0. So final potential energy will be minus g capital M small m by r e plus, that is radius of the earth, plus h. Okay, so we can see here that we can also able to cut this m, small m we can cut here. So if we cut the small m, so we will have a v square by 2, which is equal to g into m by re minus g into m by re plus h. So if we take a common from this gm, so gm will be common, so this will be re plus h minus re divided by re into re plus h. So we can take this. Okay, so we can also write here v square. Now v square is equal to 2 into gm by re, and this re got cancelled out, so we have a h into re plus h. Can we multiply top and bottom with the re? So if I multiply it with the re, here also if I will multiply it by the re, so our equation will become 2 gm by re whole square into h by, sorry, re into h by re plus h. Now can you see that this point is your the formula for the gravity, that is small g. Small g is equal to gm by radius of the earth whole square. So we can write here 2 into the value of the gravity, that is 2 into 9.8 into radius of the earth into height h divided by re plus h. I hope you have got this, and this is equal to v square. Okay, now from here we need to find height. How we will find height? Okay, we need to find height. So this is 19.16. So let us go in the next slide. 2 into 2 into 9.1x, so 19.6 into reh by re plus h. This is equal to b square. Now we can reverse also. reverse in this situation, 19.6 by v square is equal to re plus h by re. So this is equal to 1 plus h by re. This is equal to 19.6 by v square. So from here we can put here h is equal to re into 19.6 by v square minus 1. So we will put here value of re, that is radius of the earth. The radius of the earth is 6.4. 6.4 into 10 to the power 6 into 19.6 by v square, that is velocity square. So velocity, they have given velocity of the rocket as 5000 meter per second. Okay. Radius of the earth they have given 6.4 into 10 to the power 6, and the velocity is how much? 5 into 10 to the power cube. So 5 into 10 to the power cube. Okay. 5 into 10 to the power cube whole square minus 1. Okay. So when we'll calculate it, so what amount we are getting? 6.4 into 10 to the power 6 into 19.6 minus, I think we have done I have done some of the mistake. What mistake? Let us recalculate it so that we will get the perfect answer. So here we have got, so this is the RE. So whatever mistakes we have done, this is RE. So from here we can find 19.6 RE into H will be equal to V square into RE plus V square into H. Now we need to find H. So H is equal to 19.6 RE minus V square is equal to V square into RE. Now from here H is equal to V square by V square into RE divided by 19.6 into RE minus V square. Now we need to put the value so that we will get the perfect answer. So as per the question, we have got the velocity is 5 kilometer per second. So velocity, we put the velocity. So 5 kilometer per second means what? 5000 into 5000, that is equal to 25 into 10 to the power 6 into RE, that means 6.4 into 10 to the power 6 divided by 19.6 into 6.4 into 10 to the power 6 minus b square, that is equal to 25 into 10 to the power 6. I hope you can understand from here that uh, this is the calculation we can, if we took do this calculation, so we will get 1.6 into 10 to the power 6 meter as the height. Okay, but we want a height total distance from the center, so that is d. So d is equal to re plus, so the answer will be d is equal to re plus h. So re is the radius of the earth, that is equal to 6.4 into 10 power 6 plus 1.6 into 10 power 6. So finally 10 power 6 is common, 6.4 into this, so this we will get as 8 into 10 power 6. So the distance from the earth we have got as d is equal to 8 into 10 power 6 meter. So this is the final answer for this question. Okay. So I hope you have understood now. Now let us solve question number 7.18. The escape speed of the projectile of the earth is of the surface is 11.2 kilometer per second. So they have given the question, in the question they have given velocity, escape velocity, that is b as 11.2 kilometer per second. A body is projected out with the thrice the speed, this speed. So let us consider this is the body, this is the body, and this has been projected from the earth surface. Okay, so its initial velocity is how much? The body is projected out with the thrice the this speed, means escape velocity, that is 3 into velocity, escape velocity. Okay, okay, a body is projected with the thrice of the speed. What is the speed of the body far away from the earth? So what is b2? Now what is the velocity, final velocity of the body? Okay, ignore the presence of sun and other planets. Okay, so we can also use here work energy theorem only, WET. So by using this we will able to figure out the problem. As we know that as per work energy theorem, initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. But you can know that when the body is at infinity, they are telling that the escape speed of the projectile of the earth's surface is this, and the body is projected out thrice the speed. What is the speed of the body far away from the earth? So at infinity, what will happen? U final, that is potential energy due to the earth, will be 0. So one conclusion we have got, that U final is equal to 0. Okay, now let us take it initial kinetic energy. So initial velocity is 3 into v. So initial kinetic energy, we will have initial kinetic energy as half into mass into 3 v whole square, plus what is the initial potential energy? So we can keep in terms of initial potential energy as ui, and this is equal to final kinetic energy. Okay, so now tell me, can we write here 3 3 are 9? So this is 9 by 2 m ve square plus ui plus kf. Sorry, ui is equal to kf. Ui is equal to kf. Can we write here? Yes, we can write here. So sorry, kf we can definitely write like this. Now can we break this as in the term of 8 by 2 m ve square plus half m ve square plus ui, and this is equal to final kinetic energy. Now tell me, if see at the infinite, at the point where what will happen if you project any body with the escape velocity, so at this point what will happen? Total escape velocity as well as total energy due to escape velocity and energy due to gravity will become 0. Then only it will start rotating. Yes, so can we tell that half mve square, this is, and this is your ui, so this is kinetic energy initial plus ui, so this will be 0 at this point. So if this will be 0, so final kinetic energy, that is kf, is equal to 8 by 2 mass into velocity, escape velocity whole square. Yes, now we have a final kinetic energy. So let us draw a separation part. Okay, okay. Now, now we need to solve it here. So kinetic, final kinetic energy is what? Half into mass into this v2 velocity, that is v2 square, and this is equal to 8 by 2 into m into v escape velocity whole square. So you can cut this, you can cut this. So v2 is equal to root under 8 VE whole square. So this will be 2 into root 2 escape velocity. So 2 into root 2, the value of 2 into root 2 will be 2 into 1.414 into escape velocity has a value of 11.2 kilometer per second. So finally we will get 31.68 kilometer per second. So this is the final velocity with which it will move. So I hope you have got the answer, final answer. Okay. So thank you. Now we will solve question number 7.9. So before that we need to read this question. A satellite orbits the Earth at a height of 400 kilometer above the surface. So let us consider we can make a Earth. So this is Earth, and there is a satellite which is moving around this Earth. So let us consider this is the orbit at which the satellite is moving. Okay, and this is a satellite, right? So this is a satellite, and they are telling that the satellite is at the height of 400 kilometer from the Earth. So this is 400 kilometer, right? And it is being orbited above the surface of the Earth. How much energy must be expended to the rocket and satellite out of the Earth gravitational influence? So if you want out of Earth's gravitational influence, it means that the we have to make its potential energy as zero. You have to make potential energy as zero. So if the potential energy is minus 10 joules, so we have to put 10 joule as extra energy to make it zero. So that energy we want to find. We want, right? So how you will find this type of energy? Let us go step by step. Okay. So first of all, we need to find total energy at this point. So the total energy at this point, total energy, that is equal to potential energy plus kinetic energy, right? So the potential energy is minus G into M into small m, that is mass of the Earth into mass of the satellite divided by R. So which R we are talking about? So this total R, this R we are talking about, the total R. I'm not talking about the radius of the Earth. Total R will be equal to radius of the Earth plus 400. Okay. So this can be radius of the Earth is how much? 6400 kilometer plus 400 kilometers. So this will be 6800 kilometer, right? Now total energy is equal to minus Z into capital M into small m by R plus kinetic energy is half into M into V square. V is the orbital velocity. One thing we need to understand that the orbital velocity is equal to root under G into M by R. So if we put here, so what we will get? We will get minus Z M into small m by R plus half into G into M into small m by R. So finally we will get minus half G M into small m by R. So the total energy is negative. So we have to put the same amount of energy to make it zero so that it can come out from the Earth's influence. So the amount of external energy required to overcome Earth's Earth gravitational influence. So this will be equal to half into G into M into small m by R. Why? So see, this is negative. Why? I have already told you. Let us consider it has an energy of minus 10 joule due to which it is being attracted. So we have to put here 10 joules so that their total energy will become zero and it will come out of the influence of the gravitational attraction. So this amount of energy we have to put here. So we can put here half into g. So the value of g is how much? 6.67 uh 6.67 into 10 power 11 into mass of the earth is your 6.0 into 10 power 24 into mass of the object, that is satellite, is how much? They have given the mass of the satellite is 200 kg, so we have to multiply by 200 divided by r, that is 6800. Okay, so since it is a kilometer, so we will convert it into meter, so that our answer should be we will get as joule. So finally we will get 0.589 into 10 joule. So the answer is energy required, that is E is equal to 5.9 into 10 to the power 9 joule. So our final answer would be this amount of the energy which is required uh, for this uh, for this satellite, so that it can come out of the influence of the Earth's gravitational field. I hope you have understood this question. Now let us move on next question. 7.20. This is the chapter's gravitation. Two stars, each of one solar mass, that is 2 into 30 kg, 10 over 33 kg, are approaching each other for a head-on collision. When they are at a distance of 10 over 9 kilometer, their speed are negligible, that is v can be taken as 0. What is the speed with which they will collide? And the radius of each star is 10 over 4 kilometer. Assume that the star to remain undistorted until they collide. So use the known values of the g. Now let us draw the situation what they are asking. There is a sun, there is a sun, and there is another sun. Okay, and the distance between these two sun is how much? The distance between these two sun is, they have given uh 10 to the power 9 kilometer. Okay, 10 to the power 9 kilometer they have given the distance. Now at this point the velocity is can be negligible, initial velocity can be negligible. Okay, now if the speed are negligible, what is the speed with which they will collide? So let us consider when they will collide. Slowly when they will move, try to move on this direction, try to move this or position, so what will happen? They will collide like this. At this point they will collide, right? Got it? If we assume as a whole as a single mass system, so the velocity will be v. Let us consider the final velocity will be v. Okay, and the distance between these two center of mass, see here, the distance between these two center of mass is how much? C. The size of the earth, size of the sun is 10 over 4 kilometer, so this will be 2 into 10 over 4 kilometer, right? So this is the size, or this is the distance. Okay, now let us use the conservation of energy theorem. So if we use conservation of the energy theorem, so the or work energy theorem, so initial potential energy plus initial kinetic energy will be equal to, if we talk about this whole as a one system, so initial kinetic energy, initial potential energy of the all system will be equal to final potential energy plus final kinetic energy. Okay, now you know that initial velocity is 0. If initial velocity is 0, then what we can do? Initial velocity is 0, velocity is approximately equal to 0, so we can take it as 0, right? If so we can do it as 0. Now what is the initial potential energy. So this is the mass of the sun. So this is mass of the sun. So what will happen, the force what is the potential energy? So the potential energy has a formula G minus G into both the mass product of the mass, that is m into m, divided by the distance between them, that is distance between them is how much, 10 to power 9 kilometer. So we can also convert it as a 10 to power 12 meter, right? So we should take a standard one, so this will be 10 to power 12 meter, right? Now since this is 0, so this can be written as final kinetic energy. So final potential energy. So the final potential energy will be what? So the distance between them has not decreased, so the final potential energy we should write here G into product of the mass by 10 to the power see here, this is your 2 into 10 power 7 meter. So here we can write here 2 into 10 power 7 meter. So this is the final potential energy. Now we need to know what is the final kinetic energy. So let us consider they have a velocity in this direction, velocity v, this direction the velocity is v. So they're both, we are talking about both the system, we are not talking about the single entity. So the kinetic energy of each one, if you will add, so this will become 2 times. Why? Because they both have a same kinetic energy, because they have so same mass. So the velocity with which they will go will have a same velocity because of the collision. You know that the collision, what is the collision theory? Collision theory, by collision theory we can know these things. Okay, I hope you can understand this. So this will be 2 times of the kinetic energy of the each ball. So this is your half into mass into velocity square. So half got cancel out, mass got cancel out. So the finally v square, how much we are getting v square? So the v square is equal to gm. So this will go that side, so gm, which is common, so this will be 1 by 2 into 10 power 7 minus 1 divided by 10 to the power 12. Okay, so this is, see, as compared to this is very large, this denominator is very large, so we can ignore this and make it as 0. So v square will be equal to gm by 2 into 10 to the power 7. So if we put here the value of a g, so g is value is 6.7 into 10 to the power minus 11. You should memorize this. Into mass of the sun is 2 into 10 to the power 30 kg. Okay, and divided by 2 into 10 to the power 7. So 2 got cancel out. So this will be 6.7 into minus 11 plus 30 minus 7. So this will be equal to 10 to the power minus 10, not a minus, it will be 10 to the power 6. No, it will be 12. So this is a v square. So finally v will be equal to root under 6.7 into 10 power 6. So this will be equal to, approximately is equal to 2.56 into 10 to the power 6. So finally our velocity, that is the final answer, velocity with which they will collide and reback will be equal to 2.56 into 10 to the power 6 meter per second, because we have taken the measurement as a meter. So our final answer for this question will be this one. I hope you have understood this question. Let us do this question. So before doing this, we should read 7.21. Two heavy spheres, each of mass 100 kg of a radius 0.1 meter, are placed 1 meter apart on horizontal table. What is the gravitational force and potential at the midpoint of the line joining the center of the sphere? Is an object placed at that point in equilibrium? If so, then is that equilibrium is stable or unstable? We need to find this. Now we need to think about the situation. The situation is that there is two heavy sphere of each of a mass 100 kg. So let us draw this as a mass 1 and it has a mass of 100 kg. Okay, and there is another same identical sphere of a mass 100 kg. Okay, and they have a radius of 0.1 kg, are placed at a 1 meter far. So the distance between their center is how much? Their distance between the center is 1 meter. Okay, so I hope you have understood this expression. What is the gravitational force? Gravitational force and a potential at the midpoint. So let us consider this is the midpoint and the line joining the midpoint is this one. So this is the line joining the midpoint of, let us consider this, draw this line joining the midpoint of this both mass, and this is the center of the mass, sorry, center which will, that is at a center. So we need to find the force. So first of all, we need to understand the force. Whatever force, if we keep any mass here, let us consider if we keep a mass at this place, so what will happen? If this is a small m having a mass m, so what will happen? This earth, this sphere will attract in this direction, so the force due to left side mass is in this direction and the force due to this is in this direction. So the magnitude of force will be same. The magnitude of the force, the magnitude force will be same, but in opposite direction. Why? Because what in opposite direction, why this is happening opposite direction? See here, in this direction it will attract and in this direction it will attract. So the magnitude of force will be equal to g into mass of the this one. Let us consider the mass of this body is capital M, so m into small m by r square. So r is the this distance is 0.5 only. So the, see here, equal force will be gm m by r square, so both are equal. So what will happen? Net force will be 0 at the point. Net force will get cancel out, and it will be 0. It will be 0 only. Why? Because see, both the force are acting in equal and opposite direction and both have a same magnitude, so they will cancel out each other. So what will happen? No force will act on this mass, right? Now there is another part. They have told that you need to find a potential at a midpoint. Now at a midpoint there is a potential, right? So how we will find the potential? So potential is the formula for the potential is gm by r. But here, due to this mass there is a potential v, due to this mass also there is a potential v. So the total potential at midpoint, this is equal to 2 times minus 2 times g into m by r. Let us put the value of g. So this will be 6.67 into 10 power minus 11 into mass of the object is how much? So mass of the object is 100 divided by r. So the distance is how much? R is half, so this will be 1 by 2. So if we calculate this will be minus 4 into 6.67 into 10 to power minus 9. So this will be minus, when we got calculate it properly, so this will be 2.67 into 10 to the power minus 8 joule per kg. So this is the total potential. Okay, so the total potential is this. I hope you have got this. Now they are telling that is it in a equilibrium. See here, net force is 0. Since net force is 0, so it is in equilibrium. Okay, now the question is that is it stable or unstable equilibrium? Is it see here, is it at a stable or unstable equilibrium? See here, the situation will happen. See, the situation will be like this. See here, when uh, when there is a two equal mass, so what will happen if at the center of the mass both are applying a force? Okay, now suppose this mass has been suddenly shifted for a few meter only, so what will happen? There will be a more attraction toward this, and due to that attraction it will move like this, like this, like this, and it will go beyond this. It is not like that it will come again like this. The situation is like this. If you put here, so somehow if you will push this object for a little distance, then also it will come down for a long distance or long distance. So that's why it is your unstable equilibrium. Unstable equilibrium, right? So I hope you have understood this. Thank you for watching my videos. Hope I will meet again for the next chapter.